Guys, now we'll be discussing very important topic, which is about the microwave reflectometer measurement system design. So it is required to design a microwave reflectometer measurement system to measure the properties of biological tissue at a single frequency of 10 GHz. The system must measure the changes in reflected power, which is a function of impedance of the biological tissue load and characterized by a range of return loss. Okay, so the system produces the output voltages from zero bias Schottky diode detectors that provide an indication of the reflected wave and forward microwave power levels based on the tissue. Okay, so the probe will contact the biological tissue load that will produce a range of return loss. This is the return loss will be produced by the tissue, and we will be doing our calculations for both of these. The following microwave components are available to implement the design: a continuous wave 100 GHz oscillator with the output power level of -10 dBm, a low power microwave amplifier with a gain of 25 and power output at 1 dB compression point P1 dB plus 18 dB. Two directional couplers are there with coupling factor of 1 dB, 1 to 12 dB, insertion loss of 0.5 and directivity of 30 dB. Two diode detectors. This is the tangential sensitivity, input power saturation and output sensitivity, and a 2 meter length of the coaxial transmission line with insertion loss of 1.5 dB per meter. So 2 meter multiplied by 1.5, it will be around 3 dB the insertion loss total. So this is 1.5 dB per meter. We will multiply it with the meter to get the dBs. Okay, the other end of the 2 meter coaxial line is connected to 0.5 meter length of the rigid transmission line that is terminated with an open circuit so far and to form the measurement probe. So here this is the measurement probe. Here this rigid line probe has insertion loss of 0.4 dBm. So again multiplied by 0.4 dBm. So here you can see that it is a 0.5 meter length of the rigid transmission line. Okay, this 2 meter is this one. Okay, it is connected with 0.5 meter having this loss. So we will multiply 0.45 dB per meter with this meter. Half, this is half. So here we will be cutting it 0.2. Insertion loss will be 0.2. So using the components listed above, okay, design a suitable microwave reflector and provide a diagram for the overall measurement system design. So this will be the diagram here. This is your source 10 GHz and -10 dBm. This is your amplifier. So in dBs we simply add these. So -10 power will be 25 will be added. We will be getting plus 15 dBm here, right? And then we have directional couplers which are connected with the diodes D1 and D2 detectors, and then here we will have coaxial transmission line, and then a probe, and then the biological tissue. So here -10 dBm plus 25 is plus 15 dBm, and then we simply subtract this insertion loss from this. We will be getting plus 14.5 dBm, and then again insertion loss, subtract this, we will be getting 14 dBm. This is your forward power. Okay, and then here we have 14 dBm. Okay, and then 14 dBm we will be subtracting this 3 here. 14 dBm minus 3, we will be getting plus 11 dBm here, and then minus 2 dB of this probe insertion loss. We will be having ultimately 10.8 dBm at the biological tissue. Okay, now we will be calculating the reflected wave dBs or dBms. So here the two limits are, it is from -1 dB to -11 dB. So for the -1 dB we simply subtract here -1. So here we will be having here so here when this 10.8, we will minus here your we will 10.8 minus 1 here, 10.8 minus 1 we will be having 9.8. okay, 9.8 here, 10.8 minus 1 we will be having 9.8. from 9.8 we will minus this 0.2, we will be having 9.6 here. okay, from this 10.8 first subtract this minus 1 dB, so we will be having 9.8 here, plus 10.8 minus 1, it is 9.8, and then 9.8 subtract this 0.2 here, and this will become your 9.6 here. okay, then 9.6 again this minus 3, it will be becoming 6.6 here, and from this 6.6, this 6.6 we will be getting here, we will subtract minus 0.5, so this will become 6.1 dB max, and we have 6.6 dBm. This is obtained by subtracting 3 from 9.6, and then the signal, when the signal will turn here, if we will subtract 12 from it, so 6.6 minus 12, it will become minus 5.4. this is the calculation here. 9.6 minus 3 and minus 12, it will become minus 5.4, so we have here minus 5.4. now similarly we will do the calculations for the minus 11 dB. so minus 11 dB plus 10.8, it will be your plus 10.8 minus 11 will be minus 0.2 dBm, right, and minus 0.2 dBm, minus 0.2 dBm again plus this term or minus 0.2, it will become minus 0.4, and then minus 0.4 minus 3, it will become minus 3.4. here you can see minus 3.4, and then minus 3.4, when it will come here, we will subtract minus 12 from it, it will become minus 15.4. so this is, you can see the calculations, minus 15.4, and here the reflected power with the RL will be minus, and minus 1 dB will be minus 5.4. now reverse coupled signal, it will be 14.5, this is the 14.5, minus 12, this is the coupling factor, minus 30, this is D, minus 30, which is the directional, you can see here the value given as, this is the value given as the tangential sensitivity, this is the minus 30, so we will minus it, minus 30, this is minus 27.5, this is the reversed coupled signal. And worst case difference between the wanted reflected signal and forward coupled signal, so it will be minus 15.4 minus into minus 27.5, it will be 12.1 at minus 11 dB RL, and at minus 1 dB this will be minus 5.4 minus into 27, here this is minus, actually it's a mistake, it is minus 27.5, so we will be getting minus 5.4 plus 27.5, it will be 22.1 dB now. okay, so this is how we will do the calculations against minus 1 dB and minus 11 dB here. And now we calculate also here the forward electrical signal is 15 minus this 12, the directional coupling factor, this is the coupling factor 12, so 15 minus 12, that is 3 dBm here, this is the direct signal, and maximum reverse coupled signal is 6.1 minus 12 minus 30, it will be minus 35.9, and the difference will be 3 minus into minus 35.9, which is equal to plus 3 plus 35.9. so this is your 38.9 dBm. so these are the calculations for the power levels of the forward and reflected waves for both type of RL here, for both types of RL, minus 1 and minus 11 dB. So show the forward reflector power levels and arrows for the direction of power flow on the diagram performed as figure 1. Determine the amplitude of mounted and unmounted power levels measured with detector. So this is here we already calculate the mounted and unmounted levels. So unmounted signal is this, and unmounted, mounted and unmounted. Calculate the levels of mounted and unmounted. So you simply calculate the difference which we calculated above. So this is the difference, right? Mounted and unmounted signal. Find the voltage of detector diodes connected to the coupled ports of the two forward to second. The loss is -11, -1. Not the unmounted. So here we can see that the detector value which is given as the detector is 1 volt per milliwatt, and means for every 1 milliwatt of the power it will generate 1 volt. Okay, so here we see that the maximum is -5.4 dBm and the minimum is -15.4 dBm, which it will detect. Here we can see that -5.4 and -15.4. So for the -5.4, it is doing, the power is 10 raised to power -5.4 over 10. This is basically the inverse calculation, that we have the dB. This is the inverse method for going from dB to watt, right? So divide it by 10, because 10 log 10 into log of power, it gives your dBs. So -5.4 divided by 10, and then take its anti log, which is 10 raised to power, and then since it is dBm, you have to multiply with it 10 raised to -3, because the reference in 1 milliwatt, 1 milliwatt here, 1 milliwatt. So 10 raised to power -5.4, 10 into 10 to the -3, it is 0.288 milliwatt. The maximum voltage will be 1 volt per milliwatt, which is given earlier, multiplied by this milliwatt. So this is the voltage it will generate. Similarly, for the minimum values, we have -15.4 dBm, and we calculate its power level, and then we multiplied it, and we get the minimum voltage, which is 0.0288 volt. Now we will come to the second question, which is the question is based on the use of the impedance transformation equation for a transmission line with characteristic impedance ZL terminated with the load ZL. Z0, this is Z0 terminated with the load ZL. Z in length is equal to Z0 into ZL plus J Z0 into tan of beta, Z0 plus J ZL tan of beta. Okay. So the questions are: a length of coaxial transmission comprises of the two conductors separated by dielectric integral PWK with the relative permittivity. This line is short circuited at one end to form a stub filter, and the other end is connected to the main transmission line transmitter of the antenna. Calculate the length of the short circuit line or stub filter to use to filter out an unmounted signal 10 GHz. Give two other short circuit lengths if that could also be used to filter out the same unmounted 10 GHz lengths. A generator with an internal impedance is connected to coaxial transmission line. Its Z0 is 50. The far end is connected with the antenna ZL. Okay, so first we will discuss. We will go step by step for the A part 1 and 2. So how we will do this? We have this formula Z in L Z0. So and beta here is 2 pi over L, and lambda is your here C over under root epsilon R into F. And here we have epsilon R because it's not air, it's some material. Okay, so we will use this formula. Not V is equal to F lambda, it's lambda is equal to C over under root epsilon into F. F is 10 GHz, and here we have a short circuit here. So at the short circuit we have Z, its resistance is 0. So when we put in this main equation, we will be getting simply the 0 and 0 because of the ZL, and then we will be getting this Z0 cancelled, and we will get a J0 tan of beta L. And now for the lambda, it's 3 into 10 to the power 8 over under root 3 into 10 to the power 9 10 GHz. So it's 0.0173 or 17.3 millimeter, and the beta would be 2 pi over lambda. This is your beta. It will be around 363. Now the magnitude of the z in will be the magnitude of this imaginary number. It will be real part square plus imaginary part square over whole under root. Real part square is 0, so the under root cancels the square of this thing, and we will be getting this simply z naught and beta l. And this z naught is equal to zn, so this will cancel, and here we will be having 1, so tan beta l will be 1, and it is, we know that this is on the 45 degree, so this is pi by 4, beta l is equal to pi by 4, and l is equal to pi over 4 beta. 3.144 into 363, we will be getting 2.16 mm length. So if you want to use two conductors in parallel, we know that the resistance will get half. So what we will do, we will double this length, so that we get the ultimate overall length like this for the same results. So since the lines in parallel, we need to double the resistance to get the same effect. So L will be 4.32 meter. Now we will come to the B part. What is the B part here? B part is generator with an internal impedance is connected to the coaxial transmission line with characteristic number 50 on the far end is connected with the load impedance 300. Calculate the voltage reflection coefficients at generator load. We calculated this in the previous video. Provide a diagram to show how the generator could be matched to the transmission line. This is important. So for the maximum power transfer, we want to match the impedance of the source with the impedance of the load with the source for the maximum power transfer. And if the sections of the core transformer to be used to implement transfer, what is the correct impedance to transfer calculation into two quarter wavelength impedance transfer shown in the diagram part 2, and comment also this information to describe how the quarter wavelength transformer principle works. Okay, so the thing is, so this is first we will be calculating the reflection coefficients at the load end. We will do ZL minus Z0 over ZL plus Z0. So this is the transmission coefficient, which is 0.74, and at the generator side it will be ZS minus Z0 over ZS plus Z0. So this will be 0.2. Okay, at the load side we will be having a quarter. This is your quarter wave. This is your quarter wave transformer here. Okay, so this length we have installed for impedance matching. So this is your 300 and this is your 50 ohm. This is your ZX, and its formula, which is derived in the slides, it will be under root Z0 multiplied by ZL. So this is 50 multiplied 300 under root, this is 122 ohm. So this 122 ohm you will install here. Okay, so this is your one length of impedance of your transformer, quarter length transformer. Similarly, at the source end will be, this is the source and this is your characteristic impedance, so it will be this multiplied by this into under root. It will be 61.2 ohm, and it will be like this one. Okay, this is your Z0. Here we will have ZXOX1 and ZOX2. This will be around 122, and this will be 61.2 ohm. So this circuit will serve good for the impedance matching. And now with the transformer, first transformer characteristic impedance calculate like the previous formula, and then for the length we have this formula 3 into 10 power 8 10 to the power 9 4 into under root 3, so which is 4.33 mm, which is very low. Okay, so if we use here 3 lambda by 4, then we will be having 12.99 mm. Okay, this is your quarter length lambda by 4, and we multiplied it with the 3 times. So if we multiply it with the 3 times, we get 3 lambda by 4, 12.99 mm. So characteristic in second transformer will be 300 load side into 50 under root, this is 122 ohm, and 3 lambda by 4, again it's 12.99 mm. Okay, at the load end we will be having 300. So after this quarter wave transformation, what will be effect on the your reflection coefficient? This is the question. So at the load end, now we will be subtracting from 300 is 122.5. The new resistance. So it will be 300 minus 122.5, 300 plus 120, it will be 0.42. So it is reduced. Previously it was 0.7. So ideally it should be near to 0, okay, which is less than 0.7 previously without quarter transformer. At the generator we will be having 75.61.2 from the 600, which is again 0.103, which is also less than 0.2 previously calculated without quarter wave transformer. So hence we saw that the quarter wave transformer technique reduces the reflection coefficient for better impedance matching. So this is the conclusion of this assignment. So thank you very much for listening.